Swayam Prabha. Digital India. Educated India.
Good morning everyone. Welcome to Lecture 7. Lecture 7 deals with systems thinking, design and integration for tech-based and smart products. So in this lecture we'll understand what systems thinking is about. We'll look at systems design, okay, how we can design systems, and then how we can integrate them to create tech-based and smart products. So at the end of this lecture, you will be able to understand key concepts in systems thinking and key concepts in systems design. You will also be able to understand and apply concepts of systems integration using engineering technologies and in the context of new product development. So you will be able to think like a systems engineer or a systems designer. You will be able to design systems, and then you will be able to yourself integrate systems using engineering technologies, okay, and that will help you create and develop new products. So let's begin with a quote. If a factory is torn down, but the rationality which produced it is left standing, then that rationality will simply produce another factory. Okay, so if you break down a factory, but the thinking which went into creating it remains, then that thinking will produce another factory. Okay. It is a thinking that is crucial. If a revolution destroys a government, but the systematic patterns of thought that produce that government are left intact, then those patterns will repeat themselves. Let us say you have a corrupt government and there is a revolution in the public and that destroys the government, but the patterns of thought remain in the society, then the next government that comes around will again create a corrupt government. Okay. So, the patterns will repeat themselves. So, it is about changing the thinking. So, there is so much talk about the system, but there is so little understanding. So, a lot of people use the word system, but they do not really understand what actually is a system. So, this is a quote by Robert Pinsky from the book Zen and the Art of Motorcycle Maintenance. So, if you get the chance, if you can lay your hands on this book, please have a go. So, everyone gets this quote, you get the vibe behind this quote. So, this quote sort of sets the tone for the rest of today's lecture. So, let us actually look at a video. So, this is a slinky. How many of you have used a slinky in the past? Okay. So, let us see what happens. Okay.
Systems. Let's examine a simple one, a slinky. A slinky is a long, loose coil of metal or plastic that is an awful lot of fun to play with.
So, everyone saw what happened? Yeah. So, what do you think made the slinky bounce up and down? So, he placed the slinky on his hand, then released his hand and slinky bounced up and down. What do you think caused the slinky to bounce up and down? Any thoughts? But if I had not removed the hand, would it have bounced up and down? Why not? Okay, is it so? Is it the hand that is causing the slinky to bounce up and down? Maybe. All right, so interesting thoughts. Let's watch the rest of the video.
You bounce up and down like this. Let's watch again while you come up with an answer. If you said it's your hand, it's because your hand was there and you took it away. Take another look. Check this out and reconsider.
So, this is a box and take the hand away, but it does not bounce up and down, does
Clearly,
it?
it's something about the slinky itself that results in the bouncing behavior. Removing my hand released the behavior that was sleeping inside the spring. Whatever the slinky has inside, the box does not seem to have it. What is it?
right. So, it is something inside the structure of the slinky itself that causes it to bounce, right. It is not the structure of the box that is causing it to bounce. So, it is the hands that manipulate the slinky, suppress or release some behavior that is latent within the structure of the spring. Okay. So, there is something in the structure of the spring that is causing it to bounce up and down. The hands are releasing that behavior. Okay. So, there is an external force that is releasing that behavior, but that behavior is there in the structure of the spring. It is not there in the structure of the box. So, the box does not bounce up and down. So, really what we want to see is the relationship between structure and behavior. Once we see this relationship between structure and behavior, we begin to understand how systems work. How do systems work and what makes them produce poor results and how to shift them into better behavior patterns. Okay. So, we need to understand the relationship between structure and behavior. So, structure of the slinky and its behavior up and down, structure of the box and its behavior not going up and down. So, despite the hand, the box does not go up and down, because it is the structure of the box that prevents it from going up and down. So, that is why we need to understand how the systems work. So, what is a system? Well, loosely we can say that system is a set of things. It could be people, it could be cells, molecules or whatever. They are interconnected in such a way that they produce their own pattern of behavior over time. So, the pattern of behavior of slinky is different from the pattern of behavior of the box. So, there are molecules in the box, there are molecules in the slinky. They are interconnected in different ways because they are different systems and the interconnections are different and the molecules are different. They produce different patterns of behavior over time, and that is what distinguishes one system from another. So, the systems may be buffeted, constricted, triggered or driven by outside forces such as the hand in the case of the slinky and the box, but the system's response to these forces is a characteristic of itself, and that response is seldom simple. So, there is complexity in that response. So, the system to a large extent causes its own behavior. So, an outside event may unleash that behavior, such as pulling that hand off and then the slinky bounces up and down, but the same outside event applied to a different system such as a box is likely to produce a different result. So, there are some implications of this kind of understanding of systems. Okay. So, let us look at some day-to-day daily life examples of implications of the systems thinking paradigm. So, political leaders do not cause recessions or economic booms. Ups and downs are inherent in the structure of the market economy. Okay. The market economy is such that there will be up and down. Okay. So, a stock is going up, but then it does not keep going up forever, does it? Okay. So, there will be a down. If it is going down, again there is a bottom. So, there will be buyers who will come in at the bottom, there will be sellers at the top. So, ups and downs are inherent in the structure of the market economy. So, political leaders storm, something happened to the economy. So, those do not cause the recessions or economic booms. It is just inherent in the structure of the market economy. So, system there is the market economy, and that goes up and down just like the slinky. Competitors rarely cause a company to lose market share. They may be there to scoop up the advantage, but the losing company really creates its losses due to its own business policies. It is something in the structure of the organization itself that creates the losses or the profits. The oil exporting nations are not solely responsible for oil price rises. Their actions alone could not trigger global price rises and economic chaos if the oil consumption, pricing and investment policies of the oil importing nations had not built economies that are vulnerable to supply interruptions. So, it is not just the oil exporting nations that cause the price rise in oil. So, it is because the economies of the countries are so dependent on the supply of oil that the price will keep rising. So, there is something in the inherent structure of the economies of the nations that is causing the oil price rise. So, that's systems thinking, understanding what is really causing the behavior. The flu virus does not attack you. So, the viruses are always there around you. Okay. It is the conditions that you set up to flourish within you that lead to the virus attacking you. So, maybe you had contact with somebody, maybe you touched your face too many times. Okay. So, it is the conditions that you set up that lets it flourish within you, because viruses are always there around us. It's only when we let them get inside us that we get them attacking us. A drug addiction is not the failing of an individual, and no person, no matter how tough, no matter how loving, can cure a drug addict, not even the addict. Okay. So, only through understanding addiction as a part of a larger set of influences and societal issues that one can begin to address it. So, drug addiction is not just the failing of an individual, but it's all that goes on in society. Okay, like watching movies where people are taking drugs, or societal problems that are pushing people to take drugs, not the failing of an individual. Okay, and it's not easy to cure it, and it's when we understand what is going on in the larger system in the society that's causing the addiction. So, the essence of systems thinking is that you cannot understand the whole, like this automobile, by just understanding the tire, or by just understanding the seats that are in it, or by just understanding the outer body frame, the chassis. You can't understand how the whole functions by just analyzing the parts. So, let us read a story. Does somebody want to read it for me? It's the story of the blind man and the elephant. You go.
Beyond Goa, there was a city. All its inhabitants were blind. A king with his entourage arrived nearby. He brought his army and camped in the desert. He had a mighty elephant, which he used to increase the people's awe. The populace became anxious to see the elephant, and some sightless from among this blind community ran like fools to find it. As they did not even know the form or shape of the elephant, they groped sightlessly, gathering information by touching some part of it. Each thought that he knew something because he could feel a part. The man whose hand had reached an ear said, "It is a large, rough thing, wide and broad, like a rug." And the one who had felt the trunk said, "I have the real facts about it. It is like a straight and hollow pipe, awful and destructive." The one who had felt its feet and legs said, "It is mighty and firm, like a pillar." Each had felt one part out of many. Each had perceived it wrongly. This ancient Sufi story was told to teach a simple lesson, but one that we often ignore. The behavior of a system cannot be known just by knowing the elements of which the system is made.
Does that make sense? So, some thought that the elephant, so they were all blind. Okay. Some thought it was a rug, some thought it was a pipe, and others thought it was a pillar. Okay. So, everyone misperceived it. The perception was wrong. Okay. So, we are all like blind people when we try to understand a system just by looking at individual parts. So, you have to understand the system as a whole. So, what makes a system? So, a system is an interconnected set of elements that is coherently organized in a way that achieves something. There are these elements, the different parts of the car, okay, they are coherently put together. You put them all together to create this car, okay. So that it achieves something, which is, for instance, the car takes you from place A to place B, okay. So, three kinds of things make a system. One is the elements, okay. Then interconnections, the ones that connect the elements, and the third is a function or purpose. Okay, they are connected to create a function or a purpose. Make sense? So, three kinds of things make a system: elements, interconnections, and function. So, let us look at examples of systems. A school, we can call it a system. Okay. So, it has a lot of students, teachers, desks, chairs, boards, display systems, okay, a building, an assembly ground. So, all of these elements, when they are connected together, you form the school. Principal, okay. A city, again, that is a system. Factory, factory is a system. Corporation, national economy, animal, tree, they are all systems. Okay. So, they all consist of individual elements that are put together to create a system. So, what are the elements of the tree? Branches, leaves, roots, okay, trunk, fruits, flowers. So, those are the elements of the tree. They are connected together, and that's what we call a tree. So, solar system, it's made of a lot of planets, it's made of lots of comets, it's made of moons, it's made of a lot of dust and debris. Okay. So, all of that, the sun, okay, all of that put together is the solar system. Now, forest is made of both trees and animals. Okay. So, it is a larger system made of subsystems of trees and animals. Okay. So, systems can be embedded in systems which are then embedded in yet other systems. So, what is not a system? Any examples that come to your mind that are not a system? Or a food product, for instance, let us say soup. You go to the Doha canteen and you order tomato soup. Okay. So, that soup is made of what? Tomatoes. Okay. It is made of salt, some water, okay, some pepper. So, that is then, yeah, you can call it a system. Its temperature changes with time, does not it? So, what is not a system? A conglomeration without any particular interconnections or function. Okay. A blade. Just a blade. Okay. So, blade is made up of little atoms, right. So, they are from a metallic alloy, they are all connected together, right, and then it has a function, right. So, it is made of elements, there are interconnections between the molecules, and it has a function, right, of maybe cutting something, right, shearing something. So, that is what a blade does. So, and it evolves with time, because its sharpness can change with time, right. So, we can call it a system. Okay. So, let us say sand scattered on a road by chance is not itself a system. So, you can take some sand away, or you can add some sand and you still have sand on the road. So, if you take away or add football players, then that football team changes. So, it is no longer the same system, it is a new system. So, you can change a system, okay, and then becomes a different system. Or let us say pieces of your digestive system, if you add or remove anything, then again it is no longer the same system. When a living creature dies, what happens to it? It loses its systemness, it is no longer a system. But the multiple interrelations that held it together no longer function, and it dissipates, although its material still remains part of the larger food web system. Its material still, whichever living creature dies, it is still part of the larger food web system. So, let us look at some characteristics of systems. Firstly, there is an integrity or wholeness about a system and an active set of mechanisms to maintain that integrity. It is all connected to form a whole. Systems can change, adapt, respond to events, they can seek goals, mend injuries, and attend to their own survival in lifelike ways, although they may contain or consist of non-living things. Okay, so, each one of you is a system, because you are changing, you are adapting, you are responding to events, you are seeking some goal in your life, okay, you are able to heal yourself, okay, and then you are able to survive, and then you also contain of some non-living things like your hair, the ends of your nails. Okay. So, you consist of non-living things as well. So, all of these characteristics make up a system. Systems can be self-organizing, and also they are usually self-repairing over at least some range of disruptions. So, they can self-organize themselves, okay, and they can also repair themselves. Systems tend to be resilient, and many of them evolve with time, like you have evolved with time. Initially, you were born as a baby, and then you grew, now you are an adult, and you are still changing every single day. Okay. So, out of one system, other completely new, never before imagined systems can arise. Okay. So, from one system you can have other systems that are coming around. So, do not worry, the slides are on Hello IITK, you will get the slides. It is about sitting and thinking and making notes about the points that we are discussing. So, the slides you will get them on Hello IITK. So, how do we identify a system? So, I asked you a question, well, tell me an example of something that is not a system. So, how do you identify whether it is a system or is just a bunch of stuff? Okay. So, firstly, can you identify parts of the system? Okay, just like you said blade and then I identified that there are molecules in it. Okay. Do the parts affect each other? Are they affecting each other? Do the parts together produce an effect that is different from the effect of each part on its own? So, the molecules of the blade, are they producing any effect on their own? No. But when you put them together in that shape with some sharpness to it, then they are able to shear some object, right? They are able to cut. So, that is an effect that is different from the effect of each individual part of that makes up the system. And does this affect the behavior over time persist in a variety of circumstances? So, this effect does it continue with time? Okay. So, if you can answer yes to all of these questions, then it is a system. If no, then it is probably a bunch of stuff. Yes.
So, isn't the system is an abstract thing, like you said blade and then you said sand. So, for sand you can also consider it like it's made of atoms and many different compositions of various quality of sand. So, like, isn't system is an abstract thing which humans define? Okay, I'm considering this as a system and I'm not considering as a system. Like, if these chairs were to be randomly scattered, some outside, some inside, so I would have considered.
Yes. So, it is the definition that we give to a collection of objects that serves a purpose. Okay. So, if I take a random assortment of objects and call that a system, that may not have any function. Okay. So, just a chair and a fan, is that a system? Well, it depends. So, and if you want to call it a room with a chair and a fan, so the room is a system. The chair and the fan on their own are not a system. But if you put a chair and a fan together in a space and you call that a room is a system. Make sense? So, it serves a function where somebody can sit on the chair, okay, and is able to sit there comfortably because the fan is running and releasing some air that is lowering the temperature of his body or her body. Yes, you can say the fan on its own is a system, okay, and if you say just a chair and a fan, that is not a system. If I say chair and a fan, if I say a room with a chair and a fan, that is a system. A chair on its own, you can say it is a system. A fan on its own, you can say it is a system. And the largest system would be the room, which has two subsystems, which is the chair and the fan, and the air inside it, and the doors that make up the room. Okay, so does that start to make sense? So, it is good you are asking this question, because that is what is systems thinking. You are starting to think what is a system. Okay. So, sand on its own does not have a function, but when you put the sand together to make a construction site, so that then becomes the sand becomes part of a system, where it is one of the elements of the system.
Can we say it is the most?
I would not say that all primary building blocks are not systems on their own. So, the primary building block can be a system, okay. It may be also a part of a larger system. So, then it is a subsystem of the larger system. Okay. So, if you are saying, well, an atom, okay. So, if you go down to that level, but that atom is not necessarily serving a function, okay. So, you can say that is probably not a system. But when that atom becomes part of a molecule and that molecule is carrying out some function, then you can call that maybe as a system. It is the definition that you put together around a collection of objects that are interconnected to perform a function. That is what is called a system. So, they must be elements that are interconnected and they perform a function, and then we call that a system, and then we analyze its behavior. So, it shows some behavior with time. So, you might say, okay, an atom is then made up of electrons and protons and neutrons, and they are interconnected, and then if that atom is performing some function, then that atom has can be analyzed as a system. Make sense?
So like in evaluation have a use, so it might be a system. Like nothing, not a system does not even exist.
So, we define the word system to be able to analyze a collection of objects which are interconnected and which show behavior that is dynamic with time. So, we define that to analyze something. So, it is for our human purpose that we create this definition of a system, something that changes with time. Okay. So, it is definitely a human created definition, but it is something which we define to show that there is a whole that is made up of constituents, and just understanding the behavior of the constituents does not help us understand the behavior of the whole. So, yes, so that is how you have to sort of think about a system. So, just understanding the behavior of an electron may not help you understand the behavior of the atom. So, in that case you can think that an atom is also a system. It is made of electrons, neutrons and the protons, and the protons and neutrons are bound together to create this nucleus. Yeah. So, there is so much you can understand in the atom itself, right, and its behavior can change with time. You can take electrons off, you can make it an ion, right. So, then it is a different system. Okay. So, to say that the building blocks are not systems would be wrong. It would be right to say that they are elements which form part of a system. Is it starting to sort of make sense? So, it must, so system is made of elements, these elements are interconnected and then they together serve a function. So, think about it and write your reflections. I am curious to see what you write. So, you can be critical of this definition as well. It is not that you can go deep into thinking about this. So, and that will help you also develop your systems thinking. So, now let us look take a look into how we can carry out systems engineering. Okay. So, we learned what systems thinking is. Now, we will use that thinking to develop an approach to systems engineering. So, systems engineering consists of decomposing customer needs into actions or functions. So, we are getting back into product design and development. Okay. So, having understood what a system is, okay, we will use that in the context of systems design. So, we start with decomposing customer needs into actions or functions. Okay. So, take the need of a customer and convert it into an action or a function. The system must satisfy these actions to satisfy the need. Okay. So, the customer has a need, okay, that let us say a customer has a need for oral hygiene, brush and the toothpaste that he uses in the morning. Okay. So, to satisfy that need for hygiene, the toothbrush and the toothpaste together, what they do is they remove the debris from your mouth. They also act on the germs in your mouth and they get rid of them. Okay. So, those are actions or functions that satisfy the need for oral hygiene. So, system must satisfy these functions to satisfy the need. So, when you develop this system, it must satisfy these functions, and once it does that, it then satisfies the need. So, you must allocate or assign the lowest level functional requirements must be allocated to specific things or components, and these allocated functions translate into your performance requirements. So, you must have parts in your system that must carry out these functions. So, you must, to be able to satisfy these functions, you must design things or components that are allocated certain functionalities which satisfy the overall function. And these allocated functions then translate into performance requirements. So, based on the functions that you have given, the performance of your system will depend. Okay. So, how well does your toothbrush and the toothpaste, your maybe you are using some Colgate toothpaste. Okay. So, maybe it removes 99% of the germs in your mouth when you brush in the morning. So, that is the performance of the toothbrush and your Colgate toothpaste. Okay. The functions of removing debris from the mouth and killing the germs is translated into the performance requirement. Okay. And then you combine them with your design constraints to form your minimum attributes that the design team must satisfy. So, there might be some constraints for your design. We looked at some design constraints in the discovery phase of the double diamond. So, for instance, you might have the constraint on cost, you might have a constraint on material, that you might have availability of certain materials, certain chemicals to form your toothpaste. Okay. So, the cost of the toothpaste cannot be 1000 rupees for 100 grams. Okay. So, design constraints. So, performance requirements are combined with these design constraints to form the minimum attributes that the design team must satisfy. Okay. So, these minimum attributes are the requirements from the system. Then these requirements are synthesized into concepts. So, essentially this, if you think about the double diamond, this is your develop phase of the double diamond. You generate your concepts from your requirements, for the system, you then get your concepts. Then you have specialists who work together with the principal designer to ensure that the solution that you are creating in the deliver phase of the double diamond. Okay. So, specialists who work with your principal designer to ensure that the solution that you develop that meets the requirements. So, that is the typical approach that you take to carry out systems engineering. So, now we can talk about model of system development. How do you go about developing your system? So, you start with the customer need, okay, and you carry out a study of the need and the mission analysis. Okay. So, you study this need and then you analyze what is the mission, okay, that you are set out to deliver on. So, if you recollect double diamond, this is your discovery phase, you are studying the need and you are analyzing, and then simultaneously concurrently you are carrying out your requirements definition. So, there you will carry out many different types of analysis. You can carry out product requirements analysis. What is the requirement of the product that you are developing? What are the material process requirements? Okay. So, there are materials that you will process to create your product. What are the requirements of the processes? What are the requirements of the quality process? So, you have created your product, but then you must make it undergo quality checks. So, quality process requirements. Then you carry out your manufacturing requirements analysis. How will you manufacture the product? You carry out your testing requirements analysis. How will you test the product? Okay. Deployment planning analysis. How will you deploy the product in the market? The operational process requirements. So, your shop floor is operating. So, what are the operational process requirements? Logistics support analysis. How will the supply chains work? How will you procure all of the components, the materials, etc. So, you do them simultaneously. After identifying the customer needs, concurrently you are doing requirements definition and you are defining so many different things. And then once you have analyzed and found out your requirements, then you carry out your design, concurrent design. So, all of the things that you did an analysis for, you do your design, and then once you have done your design of the product and the process, okay. So, here you are doing system decomposition and requirements definition, you then do your design, and once you have done your design, then you scale up again. So, you carry out your production, integration and verification. Okay. So, here you are maintaining the engineering data from the product design, all of the data that comes out, the CAD files, the bills of materials, all of that you need to maintain that. you acquire, kit, store, move material. Okay. So, that is where you are producing. So, you need to acquire the materials, you need to kit them, you need to store them, you need to move them through the shop floor, and that is how your production is taking place. Then you inspect the product. So, you have done your quality process design, now you can inspect the product. You have done your manufacturing process design. So, you can make the product, produce the product. You have done your deployment design. So, now you can verify, test and analyze your product. Everyone understands what verification, testing and analysis is? Okay. So, you can test whether the buzzer of your car sounds. Okay. You can test whether the motors run so that it moves forward. You can test whether what it does in a crash. Okay. So, all of that is testing and analysis. Then you deploy it. Okay. You deploy it in the real world, maybe take the car out for a test ride and then send the cars out to the market, and then you refine your operational process. So, while you are doing all of this, you found out several shortcomings in the process, in the product design, etc. So, you go back and redesign and reiterate. So, you keep improving them, and all the while you are also doing logistics, okay, managing supply chain, outbound, inbound. Okay. And finally, the product system is in operation. So, you are then you have taken it into beyond the production, it is beyond the cutover. So, you are then operating it. So, the Boeing aircraft is flying, your Chevrolet car is rolling out and operating in the real world, taking people from here to there. Okay. So, the product system is in operation and eventually it will get disposed. So, this is known as a V model of system development. So, that is how you carry out your system development. So, it is a V shape, just like we saw in the double diamond, diverging, converging, diverging, converging, and you can represent it as a V as well. Everyone understands? So, we have understood systems thinking, then we have seen how to design systems. Now, we can look into integrating systems. Okay. How do we integrate? So, systems integration is a universally accepted necessity in the development of complex systems. So, when you are creating the systems, they are all complex and you want to integrate them to create these systems. So, it essentially composes of decomposing the complex problem, obtaining many smaller related problems, smaller sub problems, solution of these smaller problems by teams of specialists, and then integrating them into the original larger problem. So, there are different methods of integration that you can use. There is vertical integration, the star integration, there is horizontal integration. So, let us look at each one of these. So, firstly, vertical integration. So, the vertical integration method ties together systems necessary to serve a more comprehensive set of processes within that vertical. So, there are different systems that are tied together to create a more comprehensive set of processes. So, vertical is essentially an industry or department. For instance, accounting may be a vertical within a firm, payroll may be a vertical within a firm, or marketing may be a vertical within a firm. So, it is just like a department. So, just like in our institute, we have a department of design, department of mechanical engineering, department of computer science. Okay. So, these are all individual verticals. So, this method of integrating, and then we integrate them together to call it IIT Kanpur. Okay. So, it creates silos of functionality, okay, and those are relevant to those vertical. So, all the mechanical engineering specialists, they are grouped together in the mechanical engineering department. So, they keep doing mechanical engineering all the time. Okay. So, that creates a silo of functionality and that prevents them from interacting with people from other verticals. So, if you just do pure vertical integration, that is what happens. Of course, no organization is truly completely vertical or completely horizontal. There are levels of degrees of vertical integration, degrees of horizontal integration. So, it creates silos of functionality which are formed by composition of unrelated subsystems. Okay. So, each vertical is unrelated to the other and it creates the silo of functionality. So, these unrelated subsystems might have previously operated as standalone tools that served a specific function, but did not share information optimally. Okay. So, they may have operated as standalone tools. Okay. So, now come back to thinking of products. So, these unrelated subsystems which form a vertical. So, for instance, within the company there might be a design vertical, there might be a manufacturing vertical, there might be services, there might be accounting, payroll. So, they may have standalone tools that served a specific function and also generated data, but this optimal in vertical integration, this optimal information exchange is not there. Okay. So, if you integrate, then these tools can quickly share, update and maintain critical data. So, vertical integration leverages these separate subsystems to serve their part of a complete process within a vertical. So, vertical integration, it takes these separate subsystems to, so it integrates them to create a complete process within that vertical. And then you can have horizontal integration. It is a concept that facilitates communication across the subsystems of any vertical. So, within the department, people interacting with each other. So, they are subsystems of that vertical. So, it is more of a holistic approach to integration as it is intended for reuse of components. So, if you carry out horizontal integration, then the subsystems of any vertical, they are talking to each other and that leads to reuse of the components. Okay. So, it could be services or data. So, advantage of horizontal integration is that there is general focus as opposed to a purpose built solution. Okay. So, there is a general focus and so let us say we take we take mechanical, we take aerospace, we take design, we integrate and create department of mechanical sciences. Okay. So, that would then be horizontal integration. Okay. So, there you would have a general focus. So, it is useful if your business is looking for an incremental approach to system integration, but it is also better when you do not have all the requirements immediately. Okay, that is when horizontal integration is useful, but the disadvantage is that it requires a greater level of analysis, okay, and design upfront to ensure future flexibility. Okay. So, these people who are within the vertical, okay, but they are performing different functions within that vertical, you integrate them, then how will that help you create your final system? So, it requires a lot more analysis, a lot more design. There is also star integration. So, as you can tell by the name, so it is like a star or a spaghetti. So, it is characterized by the point to point nature of the implementation. So, here the points connect the necessary subsystems, they resemble a star, and there is this is good for technology teams who need the ability to design. So, star integration is very good in the tech sector. So, you can test many different solutions independently of each other. Okay. So, for instance, within your software development team, you might have a programmer, you might have a project manager, you might have a tester. Okay. So, you might have user acceptance testing, you might have disaster recovery testing, you might have backup and recovery testing. So, all of these are different people, and if you put them all together and connect them as necessary for a specific piece of code, okay, so they can test many different solutions independently of each other. So, that is a spaghetti or star integration. It is a poor choice if your business and requirements are constantly evolving. It is good if they are not evolving, if you already know how things function within your company or your system. Okay. So, now we have understood systems thinking, we have understood systems design, and we have understood how to integrate systems. Okay. So, now we need to apply them in the context of Industry 4.0 or smart devices. So, it would be good to have a discussion at this point, because everyone is familiar with smart devices. So, what I want you to discuss now is what makes a device smart. Find 5 examples of smart devices that excite you. Which smart devices do you already own? Okay, how were these smart devices engineered? What was the engineering process? So, think about all we learned today in the systems engineering approach and systems thinking, systems integration. How were this engineered? How were the teams put together? Okay. What role does systems integration play in the development of these devices? And is a smart device different from a tech enabled product? So, this is an interesting question as well. So, if so, how? Yes, so that is where the So, what is the difference between the smart device and the tech-enabled product? So, your washing machine also has a digital indicator, okay, and it does a lot of functions which on its own, right, including heating up the water and all of that. So, it is a tech-enabled product, and when it has an error, it will show you an error code as well. Okay, so that is a tech-enabled product. There is some intelligence that is embedded into a product, but it is not connected to the internet. Okay, but once you connect that to the internet, then it becomes circuit laundry. So then it becomes a smart device. So that may be a business opportunity for you if you can set up circuit laundry in India. See, there are so many IITs, there are so many institutions, and everywhere students live in hostels, and they are probably looking for such a smart solution. And what is the difference between a smart device and a tech-enabled product? Let's have a look. So, smart devices are typically connected to a network via, for example, via cloud computing. They talk to each other, okay? They communicate with one another. Tech-enabled products are not necessarily connected to a network, nor do they communicate with other products or services. Tech-enabled products used enhanced innovations and technology to elevate a consumer or guest's experience within a home or a hotel. Okay, so they do use innovations, they use technology as well, and they improve your experience, but they are not smart necessarily. Okay, if we say smart, that means it needs to be connected to a network. So, what is a smart home then? So, we have talked about smart devices. Let us talk about smart home. A smart home is a home or space with electronic devices and products that performs tasks either automatically by remote or touch screen or by voice command, as Raja was saying about using Alexa. Okay. So, these products are connected to other smart devices or networks. This allows them to talk with one another, to coordinate tasks more efficiently, alert you to issues or potential problems, and generally it makes your life a lot easier. So, an example of tech-enabled kitchen and bathroom products, Subham was talking about tech-enabled bathroom, smart bathroom. So, next generation of toilets, showers, faucets, mirrors are all going to be these sorts of smart and tech-enabled products. So, it has innovative features and benefits that are that elevate your everyday experiences. For instance, digital showers give you unprecedented control over your daily shower routine compared to a manual shower, and you can control the temperature as you were saying, or you can even control the music depending on your mood. So, intelligent toilets are providing better personal cleanliness, more comfort and convenience compared to traditional toilets. A voice lighted mirror lets you, somebody talked about a voice lighted mirror, you were talking about, it lets you change your bathroom experience using your voice. So, there are the consumer needs which are driving these tech-enabled products in our homes, and so they are giving you more efficiency, they are giving you this oasis moment, okay, where you can escape from the rest of the world and enjoy. And you are also getting a better sense of cleanliness, and you are also getting a space that is changing with you. So, as you are growing and becoming older and older, then your bathroom, your entire living space is adapting to that changing needs that you have with your age. So, 63% of Americans are interested in a person cleansing feature in their toilet. Younger people, the demand is even higher. They want a deodorizing system to their toilet to smell good all the time. They want motion activated toilet seats and lids. 66% of Americans are interested in heated seats on their toilets, okay, and the older people, they want it even more. So, you see the demand for tech-enabled products and smart products, and that is why you have come here to study Industry 4.0. Okay, so let's look at these smart devices, and with this we will sort of conclude. But for each device, make a list of specialists you will need to develop this product. Okay. Okay, so yes, so of these products, which one do you like the most? But all of these need many different team members to be able to create them. So for a cell garden, you would need a design expert, a horticulturist, maybe somebody with knowledge of biomedical products or biology, greenhouse workers, chemical engineers, couch coaster, you might need some materials guy, some industrial designer. For Zira, you might need some food scientists, the Cola Connect with working with mechanical, electrical, agricultural designers, mechatronics engineers. So you need a wide range of expertise to create these products, and that's why some of you have chosen to work in teams, and that's a good sign that you are trying to create products that are integration of different skill sets. Okay, so with that we come to an end of this lecture on systems thinking, systems design and systems integration for tech based and smart devices. So I hope you followed everything that we discussed today, and if you have questions you can ask. Equally you can come and discuss with me. And just a reminder, please submit your proposals for the practical project by the end of this month. So that is another 2-3 days time. Okay, it is worth 5 marks and it is either pass or fail, 0 or 5. Okay, so thanks for coming and see you all in the next class.